Good, thank you. Entonces now, in this case, any point here is UB, look, UB. When you plug it in the vector value function, give me a vector, no? And this vector represents the position vector in 3D. Indicate specific point, is the image of this. So in this case, the domain is 2D. Remember, in this case, the domain was 1D. And the represent, because it's a curve. Now, in this case, 2D, but 2D flat. In this case, no, it's curvy. Okay, so we transform this surface, you see in the UV plane, like a flat, and so maybe you can convert somehow this surface integral in double integral. Exactly, we computed before. Bam, 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 bam. The rest, you see. Okay, so now you see what I understand a little bit, but I am confused. I need to see example of the parameterization surface. I need to see example of the parameterization surface. I bring a lot of examples that illustrate very well parameterization surface. Suppose example 1. Example 1. Okay, my opinion is the easy way. Example 1 is suppose que is given this vector value function que include two parameters UV, and this is vector B cosine U, comma B sine U, comma B. And he said que B vary from negative 5 to positive 5, and U vary, U is the angle, this is the argument inside the trigonometric function, to vary from 0 to pi. Okay, so what is the representation of this? What is that? Well, I have no idea. One fantastic way. Well, you put in algebra. I want to show you how. Well, suppose by hand. Suppose que I fix B. B equal 5. Or B equal 2, 3, 4, 5. Because it's inside the domain. Look, this is the domain, no? The domain and the famous UV plane, no? But I want to see the representation in the normal X, Y, Z plane. So in UV plane, I see the thing like that. This is 0 to pi, and from negative 5 to positive 5. Negative 5 to positive 5. Okay, look like rectangular, like that. I said the domain. Domain and the UV plane. Okay, let me try to understand this N X Y Z space 3D. Okay, suppose B equal 5. Well, okay, that's my vector value function look like that. It's 5 cosine U, comma 5, because I replace B for 5, not fix it. Sine U, comma 5. Okay, this part is very, very well known for you. Okay, F5 cosine, so the parameterization, the classical parameterization. Cosine U, cosine something, and Y is equal to 5. So it's a circle. Sine. It's a circle. But this circle, the Z value is 5. So it's a circle, whose radius Fi and stay at Z equal 5. It's a coincidence in the radius and the height, you know, and the Z axis. So you are doing now by B equal 2, it's exactly the same. It's a circle also, radius 2, at Z equal 2. Suppose 0 is a point. Suppose negative 2, oh, it's exactly the same like that. Does this look like a cone? Yes or no? Well, no, I am not sure. I'm not sure because it's a negative 5. It's a negative 2. Look, okay, when you navigate, you vary, for example, B, B5, que es this line, represent in the X, Y, Z space, this. Entonces, 2, 0 is a point. Okay, this horizontal line represent in the space 3D, R3, a family of the circle. However, bueno, I infer que es a cone, but I'm not sure. Suppose I fix U. So U equal, for example, pi over 2. Oh, no, pi over 2, 0, que es 0. Pi over 2, no, 0, que es 0. Doesn't matter. Both, 0. 0 first. So the vector value function is B. Okay, take this. Cosine 0 que es 1. Sine 0 que es 0. And B. And this is a curve. What kind of curve? It's line. What line? This line. Suppose U equal pi over 2. Entonces cosine pi over 2 es 0, sine es 1, es B, B. It's another line. What kind of line? This line. Entonces es obvio. It's obvious. Now I'm sure, totally clear, that this was the parametric representation for the cone. Double cone in this case, no? And double cone because I consider positive phi and negative phi, the domain, no? So you suppose that I need only one cone, entonces I restrict my domain from 0 to 5. Okay? Okay? Everyone understand this basic idea? Parameterization surface. I explain parameterization of the cone. I promise that we cover right now, today, the most important surface that we study, no? And how you represent this surface using vector value function. And this vector value function now is different to the vector value function that we studied before because we have two variables, UB. Okay? Or not necessarily UB. This is totally conventional. UB. No, UB. Okay, in this case, I realize que B represent like a radio, no? Of the cone. So instead of UB, you can use it if you want. Totally optional. R and theta. So the parameterization is R cosine theta, comma, R sine theta, comma, R. And this is exactly the same, but instead of the traditional UB, now you're using R theta because this quantity, this letter R and theta, in my mind have more sense to understand. Entonces it doesn't matter what you don't know anything about geometry, you call like a generica variable UB. So you have some idea. So you define like a R, like a theta, whatever. By the way, one more information, one more interesting information. Well, in the GeoGebra, we have a command to indicate surface. So, what is the idea for the surface? So you put the surface in the traditional way that we are doing in explicit form using XY. Okay, your GeoGebra understand. But your GeoGebra have no restriction for the domain and suppose que es infinity, or real number. Or real number in the X, or real number in the Y. So when you put a cone, for example, like that, X squared plus Y squared minus C squared equal to 0, que es the same, it's the explicit form. Well, your GeoGebra don't truncate the cone and phi and negative phi. No, continue forever by in that direction and pi. You want to put the semicone, so you isolate. This is actually implicit. Implicit. This is implicit. Sorry, implicit form. And explicit is when you isolate. For example, C. You have C is equal to square root x squared plus y squared. This is also cone in explicit form. In this case, algebra understand is only the positive part because I don't declare plus or minus. Si I declare plus or minus, a double cone. Si it's positive, it's only a cone que open up. This is clear? I need to answer for this part. Let me see the clear. Daniel Giraldo, this is clear. Okay, Leonardo here. Jocelyn here. Ana Cruz here. David Restrepo, good. Robin, good. Victoria, good. Omar Borja, oh, good. Okay. Fiddy, Edward, Carlos Duque, Giraldo, and Ricardo. Okay, good. Okay. However, super. Okay. However, I have more for you. Okay, now in GeoGebra, for example, you have one command. Remember, we have the command curve. Okay, we use it in GeoGebra. Command curve is parameterization also, but in 1D. So you copy X to anytime, no, to T parameter, Y, T parameter, C and T parameter because it's a curve in 3D, and you define T in between one specific interval from A to B. This is the command for a curve in GeoGebra. Analogy, we have another case called surface. And surface exactly the same. You copy the expression for the X, but on 2 parameters. You copy the expression for the Y, or 2 parameters. You copy the expression for the C, 2 parameters. And you define the domain. So, for example, you vary from, I don't know, in this case was 0 to pi. B vary from -5 to +5. Entonces you copy here, the expression is B cosine U. And you copy here, comma, separate by comma, of course, B sine U, comma, and B. And you type in this in GeoGebra and you see the double cone. Let me show you. I want to show you now in GeoGebra. And also I want to send to you this script of GeoGebra in which you can see in detail at home what's the idea for this command surface. Let me try to share. Okay. Well, okay, this is this. This is the this, yes. Okay, now share screen. Okay. Switching screen. Okay, yeah, you're right. Look at that. Do you see? GeoGebra. Good. Look. Well, in this part, I'm using B and U again. I don't know why. Because I lie, I suppose. However, it's not countable in GeoGebra using theta. Well, you can, because in the keyboard we have theta. Look at the equation. The equation is surface, open the parenthesis, B cosine U, comma, B sine U, comma, B, comma, U. And you declare the domain. U is between 0 to pi, and B is from -5 to +5. And we can, in this case, I define this, but okay, we can do everything you need. For example, so you put 0 here, 0 in the domain. It's obvious that in this case we have only, okay, one semicolon. So the upper part for the semicolon. Okay. Now let me fix it again. This -5. I like this. Enter. However, suppose that you put not 2 pi. You put, for example, just pi. Right, let me remove these 2. Bang. Do you see one half of the cone, but the top part and the bottom part from 0 to pi? Wow. So we can do some surface that you never can imagine. Okay, let me retry again to pi. I want the cone, the total cone. Entonces, I encourage you to try to see this script. I want to send a link when the class is over, and you investigate, no, different surface parameterization, no. Okay, let me try. Go again to the lot math. This possible cup of water. Yeah, you're right. Okay, whiteboard now. Share screen, whiteboard. Okay, let's continue moving on to another example of the parameterization surface. Okay, another example, guys. Boom. Do you see whiteboard? That was example 1, straightforward. Now moving on to another more interesting and complicated example. Suppose example 2. But let me erase everything. You copy, right? Or you take a screenshot, you don't need that? No? I can erase? Okay, I do. Okay, and good. Okay, now let's move on to the sphere. Suppose a sphere. The classical sphere that everyone knows very well. Sphere in implicit is x squared plus y squared plus c squared equal to 4. Or whatever you want. This is x squared plus y squared plus c squared minus 4 equal to 0. This is totally implicit. Remember, implicit is, remember when you study differentiation, implicit is the function like that, x comma y comma z equal to 0. Explicit, no. Explicit is, suppose that we have c alone is equal f x comma y. No? So we are doing this. You isolate the c. The c is equal square root 4 minus x squared minus y squared. And you declare a plus or minus, no? Entonces, bueno, okay. Entonces, the complicated part or the tricky part, in my opinion, is okay, how we select the proper parameterization. How we select the proper parameterization. Because you know, okay, there are infinity possibilities to the parameterization. The parameterization is not unique. So we using explicit, we using implicit, or we declare another possibility of the parameterization because it's a sphere. And maybe it's good using a spherical coordinate. Pero no, I have no idea. I am totally lost. So I want to declare one parameterization like that. I suppose that x is x, y is y. Okay, this is two parameters instead of the famous UB. No, UB, no, y. X, so U is x and B is y. And C, no, C, no, C. Remember, two parameters. C is no C. C is this expression, que es plus and minus square root 4 minus x squared minus y squared. Our vector value function, x comma y, should be x comma y comma plus and minus square root 4 minus x squared minus y squared. And close the angular bracket because it's a vector value function. But this is not good. Not good for different reasons. Reason number one, I hate this square root. No, this is not countable for perform integration. No. Now, let's move on, in my opinion, using a spherical coordinate. A spherical coordinate is, well, you can use a cylindrical. Maybe yes, but cylindrical no good. You see the fantastic coordinate matching perfectly with the sphere is spherical, no? Spherical. In a spherical coordinate, I know. Okay, the radio, this is the sphere, by the way, and the radio for the sphere is 2, no? Because it's 4 here. So now I taking the spherical coordinate. And we're using the formulas. You don't need to memorize this formula. You have in the book, you have in any internet, and you take it. In this case, x is equal the radius 2, this is sphere in this case, is 2 sine phi cosine theta. Y is equal to sine phi sine theta. And C is 2, because the radius 2, no? Any dimension cosine phi. Okay, entonces this is our parameterization. But wait, I need to understand physically, geometrically this idea. This is my vector value function. In this case, have two parameters. The parameter is phi and theta. No, the classical UV. No. In this case, was countable. It was nice. Was fantastic. Parameterization is spherical coordinate. Okay, now we have the first component is 2 sine phi cosine theta, comma 2 sine phi sine theta, comma 2 cosine phi. Okay. However, I feel the most important is now, what is the domain? Remember, when you parameterization something, in this way, or in the vector value function, you need a specification of the domain. And the domain in this case is 2 dimension because it's phi and theta. So I need to represent a full circle. Phi vary from 0 to pi. And theta vary from 0 to 2 pi. Entonces, si ya represent graphical this domain, this is theta, this is phi. Oh, entonces nice. Because it's 0 to pi and this is pi. Entonces represent a rectangular. This is our domain of the parameterization surface. But I want to understand geometrically this. Okay, this is my sphere. Okay, I want parameterization. I prove mathematically that this is this vector value function. However, I know that geometrically, geometrically, this is my sphere. Okay, this is my sphere, like that. Radius 2, no? Radius 2. I don't need to represent XY C plane, but you can imagination. For example, suppose that you travel in the domain like that. Suppose that you travel phi equal constant. Like that, phi equal constant. So, supposition is phi is constant. I don't know si es 0, pi over 2. However, theta no. Theta is variable. The representation of this line in the 3D is something like that. Like a parallel in the, for example, in the Earth planet, the imaginary parallel line. No? However, si you travel in this direction, in which you consider que phi is variable and theta no is a constant. For example, theta 0 is the equator. Theta 0. And theta positive, like that. From 0, our 0 is here. No. It's 0 here. South pole. And the equator is pi over 2. I suppose it's the middle of the pi over 2. And 0 is the south pole and pi is the north pole. Do you understand the idea? Parameterization is fantastic. Entonces, this was extremely bad idea to parameterization. Bad idea. For 2 reasons. Reason number 1, square root, no good to integration. Reason number 2, the domain is not rectangular. And remember, the integration is fantastic when the limit is a constant. So the integration for this sphere now, when you are doing, now, is the limit is from 0 to pi in theta and from 0 to pi in phi. Es súper, es súper, es súper, es súper. Everyone follow me? Everyone follow me? The challenge is, because it's totally new, and in my opinion, it's a little bit complicated, no? So not always as easy to see. I try to cover the most important surface that we are using throughout the course. However, there are another surface that's very, very hard to parametrization. Example 3, no? 3, no 2, 3. 3. Okay, it's the famous C equal 4 minus x squared minus y squared. It's a paraboloid, right? It's a paraboloid in 3D, the famous paraboloid XYZ. This paraboloid, I know it's paraboloid because x is squared, y is squared, and c no squared. Entonces it's a paraboloid along the z-axis and open down because the sign is negative. And the z-intercept is 4. At that point is 0.0,4. And open in this direction. Shin. Okay, so well, suppose and the first octane is a circle here, and this is my sphere, my surface, sorry. Sphere, no, paraboloid. Well, in this case, the parametrization is not easy, but I want to use a cylindrical coordinate. Remember, cylindrical is good in cylinder y en paraboloid. Spherical is good in spherical and cone. Oh, actually, in cone we're using another thing, pero bueno, okay. Entonces, suppose the parameterization is R, comma theta, because I use maybe polar, no? Is R cosine theta, comma, R sine theta, comma, and C is 4 minus R squared. And the definition for the domain is theta vary from 0 to pi, and R vary from 0 to 2. How do you know get 2? Well, 2 is this radius, no? This point is the point 2, and it's a 2 also, no? The radius 2 in this example. And the domain for this parametrization in the famous theta R plane is also rectangular, and rectangular vary from 0 to pi, and from 0 to 2. Okay, this is my domain, que represent under this vector function transformation point by point of the paraboloid. Okay. And you put in your algebra like that, and you see your famous paraboloid, and at least the portion of the paraboloid you want. For example, I want to illustrate something. Suppose the point 0,0 here, 0,0 in the domain. And so what is the representation 0,0 here in the R3, in 3D? Well, entonces R 0,0 is es 0R 0, 0, es 0,0,4, no? Because it's R, si R is 0, this is gone, this is gone, this is 4, and this is this point. Okay, this point, sorry. This point. Point by point, we can find the image inside the parabola. Okay, super. Everyone follow me with the paraboloid? The thing we are doing is parametrization surface. that the classical parameterization, you know, or you memorize in explicit or implicit form. Now we see another point of view, que es parameterization. And parameterization opens the door to the new thing, okay, to see the surface. Example 4. Example 4. In example 4, we have cylinder. Wow, cylinder. Cylinder. Suppose parameterization this cylinder. X, Y, C. Suppose cylinder like that. Oof. Suppose cylinder like that. It's completely full cylinder, pero okay, is the radius 2. And the height of the cylinder is 10. Okay? So this is the surface I want to parameterization. Look, this is the surface. Okay, I want to parameterization. And the parameterization is, when I use it again, cylindrical coordinate. In cylindrical, I had declared, for example, is r theta. I declare the x component is 2 cosine, because you know very well, hello, okay, x equal to cosine theta and y equal to sine theta represent in 2D a circle, that circle, look. Comma 2 sine theta, comma, I put r, but actually it's not r. Let me put another letter. Let me put maybe, because r is a constant, r2. So no good r. So you declare the name you want. So this variable is no radius. This variable maybe I suppose que the height is h, no? It's h. Entonces this is h. And this is the parameterization. Entonces you declare the domain. Bueno, the domain is clear que es theta vary from 0 to pi. Because it's a completely circular cylinder. And h vary from 0 to 10. And this is the parameterization of our cylinder. Entonces the parameterization is theta in this axis, h in this axis, 0 to pi in this axis, and 0 to 10 in this axis. And this represent the domain in the h theta plane, que es rectangular. This is the idea. Try to, so what is the good parameterization? The good parameterization is you try to do an easy way. You adaptate according to the geometry of the surface to the most comfortable coordinate, parametric, cylindrical, or spherical, or Cartesian XY, depending. There are other progress much better parameterization XY. For example, plane is obvious, is much better parameterization in the Cartesian coordinate XYZ. This is the example of the cylinder. Okay, of cylinder. Okay. Let's see another example, a little bit more complicated. Suppose example 5. Parameterization ellipsoid. Ellipsoid, for example, in implicit or explicit form is 9x squared. Suppose this example, plus 4y squared plus c squared equals 36. Wow. So this is identification. Wow. X, Y, and C is completed. Everything is a square. Everything is plus. This is ellipsoid. And the fantastic way to understand much better the ellipsoid is you express it in standard form. You divide by 36 everything, because the right hand side must be 1. So we have here x squared over 4 plus y squared over 9 plus c squared over 36 equal 1. This is equivalent to say x over 2 squared plus y over 3 squared plus c over 6 squared. More clear now. And so now it's a moment to make a decision what coordinate we use into parametrization. I suppose it's spherical. It's spherical because the sphere and the ellipsoid are family, ¿no? Entonces, spherical, entonces en the spherical, I suppose que x is equal, look, x is equal 2, que es the number here, 2 sine phi cosine theta. So the parameter, in my opinion, is much better, is spherical. In spherical phi and theta. So basically, the two parameters we use in spherical, they are angle. Two angle, no UV, two angle, phi and theta. Y is 3. Oh, because it's different to the sphere. 3 is the guy here. Entonces, again, sine phi, sine theta. And 6 is this number, que is 6. Cosine. Cosine what? Cosine phi. Now, if you, for example, plug it in this expression here, look at that. So this is u divided by 2, no? U divided by 2 and a square. So you have sine phi square cosine square theta plus divided by 3 now and a square. We have sine phi square sine square theta plus cosine square. So divided by 6 and square cosine square phi should be 1. Well, so you see que sine phi is common factor. Look at that. We factor out. Sine square phi, paréntesis, cosine square theta plus sine square theta. But this is 1. You know very well this identity. So finally, we have sine square phi plus cosine square phi. Wow, it's 1 again. Okay, this is fantastic. Entonces, the vector value function to define ellipsoid is r phi comma theta, and the x component is 2 sine phi cosine theta, comma 3. Look at ellipsoid, different coefficients. That is the reason. It's no equal radio. It's not sphere. It's ellipsoid. Sine phi, sine theta, comma 6 cosine phi. And now, if you know, I need to define the parameters. So phi vary from 0 to pi, exactly the same with the phi and theta. Go from 0 to pi. If you want the full ellipsoid, no? And the domain representation for this is easier. It's exactly the same with the sphere. Theta phi from 0 to pi and from 0 to 1 pi. A rectangle. Nice. Do you understand very well this or no? I try to bring some example, no, of the parameterization. Suppose I try to bring some example of the parameterization. For example, hyperboloid, 1G hyperboloid, it's more complicated. If you want, I can explain, but no today. Okay, now I bring on one more. Okay, I suppose it's good, interesting, because we need to use it, I suppose, in one more. It's the last example, the last example of the parameterization surface, is example 6. Example 6, is about a disc. Well, this is a circle, or not necessarily a circle, but should be elixir, but elixir in 3D. Suppose que I am doing the parameterization one surface. It's not clear the explicit formula. No, because it's the intersection to thing. For example, you have the x squared plus y squared equal 1. It's a cylinder, right? And we have a plane, this is y plus c equal 2. So my surface is the intersection, it's the common part in between the cylinder, solid cylinder, and the plane. So I try to use my imagination. My imagination is, look, this is x, this is y, this is c. We have cylinder like that. Okay, the radius 1, because the radius 1 cylinder, and we have a plane. This plane is look like C CS0 Y2 and CY0 CS2. It's a plane like that. Plane passing through this line. It's a plane like that. And the intersection, wow, no good. And the intersection between the cylinder and the plane, I suppose, I try to do my best, guy. Okay, is something like that. It's like an elixir like that. Entonces I want to parametrization this. No circle, is this, because it's surface. You know, it's the common part. Suppose the cylinder is solid and cut off by the plane. It's obvious the intersection between solid cylinder and the plane is elixir, no? But no elixir, because elixir, when you're talking about elixir, is a curve, it's only the outer part. No, it's solid. Entonces, what's the name of this? What is this? It's this. Entonces, we have different this. We have circular this and elliptical this, no? Entonces, the parameterization is, well, in this case, I'm using the cylindrical, no? It's r comma theta is, you know, the x part. Okay, the x part. How do you know the x part? Well, the x part comes from of this part, because I know the famous parameterization x equal r cosine theta, like a polar, no? R sine theta. But in this case, r is variable, because it's not the same r in the center of the disc and the border of the. Okay, this is r cosine theta, good, comma, r sine theta, good. This is the x component of the disc. This is the y component of the disc. And the z component, well, the z component is I try to get for this equation, no? State the relationship C, you isolate z is 2 minus y. Is 2 minus y. And who is y? Well, y is r sine theta. Entonces, the C formula is 2 minus r sine theta. And close the parenthesis. This is the C component of the parametrization of the surface que represent this. And that's it. No, I need to represent the domain theta vary from 0 to pi, because I want the full circle, totally circle, not this, sorry. And r go from 0 to 1. Is the radius of the solid cylinder, because the solid cylinder is bounded like this. Wow, fantastic. I like that. Do you understand very well or no? Do you understand very well parameterization surface? Little bit, you know, this is just the beginning. So in the example of the application, you see. Pero es open the door for the new possibility, no? To see the surface that you never see before in your life. Parameterization surface. You see parameterization curve, pero parameterization surface never you see. Okay, guys, so we studied the last kind of the integral. It's the surface integral. Surface integral. I promise it's the last one. The rest of the course is the theorem que connecting different integral, like a green. Remember green theorem connecting double integral and line integral. Okay, we study another theorem. But definition surface integral. Look at that. Definition first. I need to understand what means that. Suppose we have the three axes, x, y, z. We have surface, okay, like that. Yeah, I can do the parameterization of the surface. Okay, I have the parameterization, so we will be able to represent this surface like that. UB, okay, put the generical UB. Is vector value function, look. Is x, u comma b, comma y, u comma b, c, u comma b. And you define, of course, different domain for u and b. And 2D. UB, sorry. UB. Suppose that you are doing good parameterization. Si it's good parameterization, then it's rectangular. Because you select properly. Si es cylindrical or spherical or Cartesian, doesn't matter. Entonces you have the U vary from something to something, A to B. This is A, this is B, and B varying from C to D. I have perfect parameterization for this surface. C to D. Okay, entonces definition de surface integral. This is the new idea. Bueno, eso always, the notation is like a double integral. Why double integral? Because this object is 2D. Surface is 2D. So surface have length, width, but no height. It's totally negligible. No solid. This is not solid. It's totally, it's flat, pero could be flat. It's not like a double integral. Double integral is like that. For example, double integral is in the xy plane. This is flat. This is flat. I suppose C is 0, or C1, or C2, but in this case, no, it's variable C. A double integral is, suppose you have a function G, capital G represent the integrand function. And this is ds, capital S. Well, some book call different. Call like that the sigma, another call dsa, que surface area. I don't like this way. I like to call the capital C, que is completely different to ds when you are doing the line integral, because this is s, little s is r length, and this is not. This is surface. It's an infinitesimal element of the surface area. And you put it here as similar to the line integral, you put C, something like that, 3D or 2D, depending. This is line integral, this is surface integral. So what is the representation? What mean that? Well, it's Riemann-Zone. Any integral de Riemann-Zone. Entonces, el Riemann-Zone es el límite cuando delta S approach to 0. Entonces, who is delta S? Bueno, delta S, this is an element. An arbitrary element. Delta S. So when you are doing too small this division, and you are doing the summation, Riemann-Zone, every pieces, okay, you define inside the surface, and you evaluate the function G, que is the integrand function, in totally arbitrary value, que normally everyone we call X after, Y after, and C after. They call after because it's weird. So you select here inside, totally arbitrary point, and this is the after point, a multiplication by the delta S. Okay? G is the function that you are doing in the integral. And now, so I want to show you how we convert this surface integral in one double integral. Similar idea that we are doing when you convert line integral to the regular integral like a Cal 1. But first of all, interpretation. What means surface integral? Well, so you suppose that function Suppose que that function is the density function to get some interpretation. Entonces, this integral is the mass of the hypothetic surface. Okay, I repeat again, guys. This surface is, so you assume que the thickness is totally negligible. It's not solid. It's not like a triple integral. Triple integral, you suppose que es solid. And the surface integral, you suppose que es a lámina, pero curvilámina. But however, we have mass because we have density. In this case, density is the mass, kilogram, pero per centimeter square. O sea, es surface. Entonces, the unit for ds, I suppose, meter, no centimeter, meter much better, more elegant. Meter square, and it's a meter square. And this cancel out, meter square and meter square, when you multiplication, and the answer is kilogram, que es the mass. Okay, this is a hypothetical case in which the integrand function, capital G, is the density function. So we can find, for example, another quantity like a center of mass. So it's different. You know the expression for this. One important, at least today, is when the capital G function is 1. You see, so we have surprise always when it's 1, no? You remember, for example, when you study double integral, and the integral function is 1, so we compute the area using double integral. However, when you using triple integral, and the integral function is 1, is a volume. And the line integral, when the integral function is 1, actually is the arc length. However, in the surface integral, when the integral function is 1, the meaning of this is surface area. So you want to find surface area, you assume that the integral function is 1, but actually the thing we are doing is surface integral in the ds. And this is SA, surface area. Okay. Entonces, today, with the email, I send the link to connection for the Skype. I send one document because this is very complicated. There are many options. I try to present to you, I don't know if today or we continue Friday, the different possibility to compute the surface area. Con surface area, no, sorry, the integral line, surface integral. This is a flow chart can illustrate different ways. So, but there are many ways to say you don't know. Professor, what formula are you using? I have no idea. You actually we can use either, and the answer is the same. But there are one way is easier. So computationally is easier than another. I anticipate, guys, que en surface integral the integral is heavy. Not heavy the integral, sino heavy the algebra behind this. Okay. Suppose que I make a decision to compute the surface integral using parameterization. Okay. And then I know very well the parameterization. The parameterization is R, U, B is equal to something, no? X, U, B, Y, U, B, C, U, B. So when you are doing the parameterization, so suppose, you understand this. Suppose I have suppose que I am doing a zoom of this surface. Here, zoom. Entonces I saw in this zoom a lot of line like that. And like that. And this corresponded perfectly to the one domain of this. So I want to represent graphical UV like that. This is my region R. This is my surface S. And you know that there are connections in between these using this vector value function. Okay, now my goal is determine the surface integral. Suppose assume that this square is this. Yeah, actually this is not square, rectangular, and this is totally no flat. Maybe it's a little bit curvy like that, no? So now, in order to find the relationship between this guy, I assume, for example, at this point, okay, this point, this corner, I assume, let me use another color. So I compute this vector. Okay, this vector is Ru. So you differentiate the vector value function with respect to u, and you obtain like one tangent vector, no? Tangent vector, okay, is parallel to this. However, si you differentiate this vector value function with respect to b, you obtain, okay, I suppose that this curve is from different u value. You say u1, u2, u3, and so on. Different u. However, in the other direction, b1, b2, b3, b4, b5. So when you compute it, now if you multiplication Ru cross product Rb. But wait a second. My goal is to determine ds, differential ds. What is the relationship between ds and dA in this region? This is my goal. Entonces, this vector, okay, I need to find the area of the parallelogram. I know in the first lecture, the interpretation cross product is the area of the hypothetical parallelogram that this vector expand. Pero okay, pero no totally Ru, it's Ru du. Du, because I want to find elementary small here. Parallelogram. And this is dV, the RB, dV. So basically, the dot product I want to perform is Ru du. It's a vector. Cross product. RB, dV. Okay, this guy, and this guy, I suppose is a scalar. I put outside the dot product you have. Ru cross product RB du dV. Now you find the magnitude of this. Remember, is the cross product is a vector, but I don't care the vector. I need the magnitude of this because I want to find ds. Now my conclusion is ds. So the differential, the elementary infinitesimal differential of the surface area is equal the magnitude of this. And this is the formula that we use to compute any surface integral. Okay. Let me set up the surface integral. This surface integral is a formula, guy, que es g en x, y, z ds. We transform a little bit to the double integral. Wow, double integral, but double integral where? In the region R. So I translate the problem, complicated problem, in x, y, z plane, the surface, and another easier problem, and UV plane, que is two-dimensional, no? And this is a double integral. Double integral of what? Of the function g, evaluate r, the vector value function, that is r, u, comma b. This is one notation, no? To indicate this. We can put instead of x, y, and z, you put this, and this is the same thing. And ds is magnitude RU cross product RB TUDB. And this is the formula to compute the surface integral when you have in your hand the parameterization of the surface. Okay? Pero no, it's the only way. No, there are 3 different ways. I want to explain right now. So we have, for example, suppose we have no parameterization, or it's super complicated to find parameterization. There are another way, yes. They are the explicit form. Explicit form. The explicit form. In the explicit form, I assume that we have the formula C is equal fx comma y. So we have no vector value function. We have the equation of the surface. No in vector value function, like that, like a classical, like we studied before this lecture. Well, okay. So say we can parameterization, but we can parameterization using xy. It's like a natural. O no natural, sino es de Cartesian, ¿no? Entonces yo asumo que x es x, y es y, and c es igual, c es igual a f en x como y. Okay, entonces now I have a vector value function now, no in the super elegant way, sino en explicit form, que es x, y, f, x, y. Okay, paréntesis, and angular bracket. Yeah, I apply that formula, or I try to apply that formula. In that formula, I compute the Rx. So you differentiate with respect to x. Okay, so big as 1, 0, and fx. So derivative x with respect to x is 1, derivative y with respect to x is 0, and derivative this function with respect to the partial derivative of the function, que represent the curve, is our surface, no curve, surface, with respect to x. Likewise, you differentiate with respect to y, que is another parameter that we are using, we have 0, 1, and fy. And when you perform the cross product, and between this partial derivative of the vector value function, okay, you copy here I, j, k, the famous I, j, k. You put here 1, 0, fx, and you put here 0, 1, fy. I want to skip that part. You know very well the answer is minus fx, comma, fy, comma 1. This is the vector. If you want to find the magnitude of this vector, magnitude is square root, this guy square, so the negative is gone, this guy square, sorry, this is minus, both minus, but when you square positive, plus 1. Therefore, using this idea, our surface integral, we can set up like that. Surface integral in the function g, x, y, z, yes. Remember, g is the integrand function. This is no integrand function, it's the surface. So we start always analyzing the surface. In this moment, I come back to the integral, and I convert this surface integral like a double integral in the region R. So in the region R, okay, by the way, this region R is on XY plane, no? So this is not the problem I investigate how. Look like because I have no information about the function. So you replace G, plugging in, X is X, Y is Y. C no, C is f of X, comma Y. Okay, and ds. Look, ds is ds And our example is square root fx squared plus fy squared plus 1 dx dy. Because I suppose the parameter, okay, I suppose in the parameterization was x and y. Entonces, you replace dx is now square root partial derivative of the function que represent the surface with respect to x plus partial derivative with respect to y plus 1 dx dy. And now, entonces, now it's easy. Well, easy, no, because this is a horrible algebra expression, no? The integration may be super complicated, no? But this is at least the theoretical formulas. Okay, you need to make decision. See, you are doing a special parametrization using UV or R theta, whatever, depending the geometry of the surface, and the Cartesian, the regular Cartesian, XY. And only XY? No, because similar procedure, okay, I don't want to prove again, we can use in suppose that we have the surface in different, explicit also, but in this case, Y is isolated. In this case, bueno, X is X, Y is no Y, is the function, que I call different, no F, I call H, and C is C. And the formula is very similar. It's double integral in the region R, but this region R now is on XZ plane. Entonces, in the integrand function, we have X, stay the same. Y no, Y is H, is comma C, and C is C. And the ds is exactly the same formula, but you differentiate H in X squared, H in Y, and Y no, and C. And C. I copied wrong in my paper. Square plus 1. In this case, differentiates dx dc. Do you understand? It's exactly the same. We have another possibility, of course. We have the possibility in which we have, for example, x. So in our original surface, instead of isolate the classical z, you isolate y or you isolate x. Because, I don't know, because maybe it's countable algebraically. YC. In this case, it's the same, no? In this case, x no x, fp. And the parameter I'm using is y and c. Y, c, c. And the double, no, the surface integral is possible doing like a double integral in the region R. In the region R lie on YC plane in this case. And also the integrand function is g and p y comma c comma y comma c multiplication by partial derivative p, que is this p, with respect to x, with respect to y, sorry, plus partial derivative with respect to c squared plus 1 dy dx. Professor, they are in that part. Yes, this is the complicated. That's the reason I sent the flow chart. Okay, a little bit indicate, but no, don't worry. We are doing example. In the example, you see a little bit what's the best way, and you eliminate some stupid formula, no? Okay, this is explicit. So far, we studied parametrization, we studied explicit, and now we study implicit. Let me explain implicit. Implicit form of perform surface integral. Implicit. But let me erase everything. I can erase, guy? Or you don't need to take a screenshot? No, it's too long, no? Wow. Okay. All good. Okay. Let me try to explain implicit form. Implicit. It's another way. I try to illustrate example. Implicit form. Implicit form is que my surface is expressed like that. And it's relatively easy. Suppose that you have C equal f of x. This is explicit, no? How will you change to implicit one? You subtracting. This is f x comma y minus c equal to 0. No. And you assume that this is my capital F x comma y comma c. This is very straightforward. So there, however, it's important using maybe this. Some people prefer implicit. Let me try. Okay, to derive the formulas for the implicit one. The thing you should do is you compute the gradient of this, and the gradient is partial derivative of the component with respect to x, the first component, partial derivative of capital F, que es implicit form, capital Y and C. And also, suppose que I make a decision, convert the surface integral en doble integral, pero en xy. Si es en xy, so you take the gradient. We are doing the dot product with the k. Que es the vector que es perpendicular to the xy plane. Okay, this is my C, and this is my k, unit vector. So when you are doing this dot product, it's obvious. Okay, we have only the component FC. Is this? Because k is the vector 0, 0, 1, no? When you perform this vector times this vector, the only guy that stay alive is the third one. Here, if you divide, division, let me derive the formula. The formula is, look. This is the crucial moment. The formula is, you take the magnitude of the gradient. The magnitude of the gradient is the square root f of x squared plus f of y squared plus f of c squared, and you divide by magnitude of the gradient, pero the component k, que is just f of z. You introduce this f of z inside the square root, you have that f of x divided by fc squared plus fy divided by fc squared plus fc divided by itself squared. Que es obvio que this guy is 1. Entonces, I suppose que you remember the formulas que we studied in the chapter to find implicit differentiation. And I suppose que you remember that formula. Partial the f with respect to x is equal minus f of x divided by fc. This is exactly the same, this guy but a square. So this is equivalent to say f of x squared plus fy squared plus 1. Wow. And this is multiplication by dx dy because we're using the k component. And this is this, d capital S. So I derivate in that part que this expression is equivalent to this expression que we very well know in explicit form. Entonces, what is my recommendation? Well, my recommendation is doing the surface integral. I'll say the surface integral and g x comma y comma c ds in this way. Well, you copy double integral in the region R. You copy g, evaluate in the function, in this case x comma y comma c. But ds now is a magnitude gradient divided by magnitude gradient f Okay. And this is dx dy, double integral. If you replace k for I o for j, entonces in this case for I is, let me see, I es this direction, entonces es YZ plane. Entonces we have, so you have this is d dy dc, and j is dx dc. Okay, this is another formula. I don't want to repeat this stupid formula one more time, taka, 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 because, pero es another possibility. Okay, super. I bring in the time we have at least one example. At least, but let me, well, okay, it's okay. Let me copy here one example. Example one. Easy. Example one always is easy. I try to make easy, or try to find easy. No? Example one. In the example one, we have a surface. The surface is represented in that way: x squared plus c squared over 4 equal 1. Okay. But I want to compute the surface area. So far, compute surface area. The surface area, I suppose that the function g, x, y, c is 1. And the thing we are doing is double surface integral this, because my goal is find surface area. Entonces, one possibility is parameterization. Okay, what kind of surface is? Help me, guys. What kind? So you don't need to know parameterization, nothing. You identification the surface exactly the same we studied in the chapter 1. What kind of surface? X squared, c squared, cylinder. Very well. A cylinder. Gerardo. Along what axis? Along y, que es the axis que es missing. The variable que es missing. So basically, it's a cylinder. Let me try to represent, because one picture is much better than 1,000 words. Okay, we have something like that. X, Y, Z. I forgot to say something, no? Important. Okay, the parameterization, when you are doing the parameterization, you have not the total cylinder. We have one portion of cylinder. The cylinder actually is not circular cylinder, it's elliptical cylinder, right? Something like that. Entonces now I want to find the surface area. So this area. No, the top, bottom. No, this is easy. No easy, pero es no important in this problem. The surface area I want to compute is this surface area. And this limit, o sea, en y, is along the y, y go from -1 to +2. So this point is -1. So this plane is the plane y equal -1, and this plane is y equal +2. Okay, entonces the parameterization of the cylinder we studied a little bit before, no? Is suppose que I call vector value function is t, y. So I declare two variables, t and y. Who is t or theta, whatever you want to call, just matter if it's cosine t, comma y, comma 2 sine t. Where come from this? Well, I study here in the equation, x squared plus y squared over 4 equal 1, x squared plus y over 2 squared equal 1. Entonces ahí declaré que, dice sí, sorry, coño, sí. Ahí declaré que x es cosine t, and c is 2 sine t. Look, to make clear que the famous trigonometric identity, no? Cosine squared plus sine squared equal 1, no? And this is the component I put here, tan. And why no? Why it's totally free? So now, my definition of the parameterization this surface is T vary from 0 to pi because it's full cylinder. But why not? Why vary from -1 to positive? Okay. And thus I have clear like water, in my opinion, no? You let me know if it's good or not. The parameterization of the surface. Okay? Parameterization of the surface using two parameters, T and Y. I call T, and suppose one student say, no, I don't like T, professor. I like theta. Well, put theta here, it's the same. And theta in the domain. Okay, so now what is the next step? Well, the next step is compute the cross, o sea, partial derivative of the vector value function with respect to T. Derivative cosine is minus sine. Derivative with respect to T is 0 because the second component does not depend on T. And the other is 2 cosine. 2 cosine T. Okay. Now partial derivative with respect to Y. Well, this is 0, not depending on Y. This is 1, depending only one Y. Derivative Y with respect to 1 is 1, 0. Okay. Now cross product. Always the same. Always is the same. Cross product is cross product. It's cross product T cross product RY is IJK minus sine T 0 2 cosine T 0 1 and 0. Now I perform double. I omit that part. The answer is minus 2 cosine T, comma 0, comma minus sine T. Now I compute the magnitude of this. The magnitude is a square root. Each component 1 by 1 square. Entonces 4, 2 square 4, cosine square T, plus sine square T. You can manipulate a little bit algebraic, yeah, we can. Because I break it down, this 4 and 1 and 3. So 3 cosine square T plus cosine square T. This is more elegant. And you know that square cosine T plus sine square T is 1. This is my final answer. My partial answer is 3 cosine square T plus 1. Then, to find the surface, well, the surface is surface integral ds is equal. Now, double integral in R. Okay, but who is R? I am lost. Who is R? R is the parameterization we are doing before. Look at that. R region is T, Y. Sorry. Relax. Okay, good. This is T and Y, is my two new parameters, no? And the parameterization is from 0 to pi, and Y go from -1 to 2. This is my region. This is my domain. In the YT domain. Okay. And this allow me, this is my region R. Okay, I convert this surface S in 3D and this region R in 2D. But in the hypothetical plane YT. Okay, so now what should I do? When I replace this, I put square root 3 cosine square T plus 1. And the differential is obvious que es dy dt or dt dy. It doesn't matter, whatever you want. No? What about the limit of this? Well, wait, let me copy again. Double integral. The integral function is 3 cosine square T plus 1. I assume dy, yeah, in this order, dy dt. So I integration in this direction, guys, like a double integral. Entonces es from -1 to +2, and this is from 0 to pi. Bang! This integral is a little bit complicated. So es, bueno, you put in GeoGebra, or you put in, no, in Wolfram Alpha or in the graphic calculator, no? Because it's a little bit complicated. And the answer is approximately, when you put it is, see, the answer is not exact, it's 29.0653. And this represents the surface area of this. Okay. Then you say, no, Professor, but this is too complicated. I know it's too complicated. Too complicated. Maybe I am doing using geometry, no? In the geometry, I know that the surface area for the cylinder is like a multiplication. The time is over. This distance, okay, by the way, is 3 multiplication by the r length. In this case, it's not circular, it's elliptical. But entonces now, we are using r length formula. Entonces, r length formula belong to the line integral. Entonces, line integral, you parametrization, this line, pero with respect one parámetro que es t, porque es el curve. Entonces, this is cosine t, 2 sine t. Exactly the same we are doing here, pero only this component. And you differentiation this, que es minus sine and 2 cosine, no? You find the magnitude of this. You see it's very, very analogous. It's a square root. And we have the famous 4 cosine square t plus sine square t. Okay, I manipulate a little bit, que es square root 3 times 3 cosine t plus 1, no? Entonces now, in order to find the r length of this, the integral, in this case, pero it's a line integral, but we can use in the parametrization, okay, t vary from 0 to pi. So because we're using the regular integral, tal 1. This is from 0 to pi, or the square root 3 cosine squared t plus 1 dt. And this look like similar for this part. Look. The only difference is, remember, this integrand function depending only of t, not depending on y. When you integrate dy, evaluating between 2 and -1 is 3. 3 is this distance. So we get exactly the same answer. Okay, using geometry, and we're using calculus. Okay, guys, I know that part is super complicated, too long, complicated, because we have a lot of